So first of all, we need to define what is the meaning of equilibrium. So a charge will be said to be in equilibrium if due to the net electrostatic force which is present on the charge, they all cancel off in such a way that the net force is equal to 0. There can be n number of charges in the vicinity. Yes, all of them will be applying a force. They can be a force of attraction or repulsion, that depends upon the nature of the charge. But if the net force is equal to 0, we will say that the charge is in equilibrium. No problem. Okay. Now, equilibrium does not mean that if you displace it from its mean position, it's going to come back, because we have seen that there are types of equilibrium. There was stable equilibrium and there was unstable equilibrium, right? So if I talk about stable equilibrium for a charge, then what I can say, that when a charge is displaced slightly from its position, the net force acting on it brings it back to its initial position, and it is said to be in a state of equilibrium. Okay, all right. Now let's understand this, that how it happens actually. All right, we'll take a system of three charges. This, at point number 1 we have placed a charge q. At point number 2 we have also placed a equal charge q. Both of them are positive. And at point number 3, which is exactly at the center, of course we know that if both the charges are equal, and if this capital Q charge is at the center, at the midpoint of these two charges, definitely the net force on it is going to be equal to 0. We know that, right? Okay. Now we say that these two charges are fixed. And the charge on point number 3 is free to move. It can move. We are going to analyze, is it under stable equilibrium or is it under an unstable equilibrium condition? Okay. So first of all, we analyze this by saying that what is the net force at this point when it is exactly at the midpoint. So we know that the charge which is present at point number 1 is going to repel this in this direction, and the charge which is present at point number 2 is going to repel this in this direction. Correct? Okay. Let us say the distance is equal and it is equal to r. So what will be the magnitude of the force? So this is force because of 1 and this is force because of 2, of course. Okay. So we know that at the midpoint F1 is equal to F2. Correct? Right? Because you can see K, F1 is K small q capital Q divided by r square. This is equal to K small q capital Q divided by r square. Right? Both of them are equal. No problem. Equal in magnitude and opposite in direction. So what is the value of the net force? Of course, the value of the net force is equal to 0. Now we will start our analysis of equilibrium. If this charge has to be in stable equilibrium along the line joining the two charges or the three charges along this line, okay, then if I disturb it slightly from its mean position, the net force should be acting in such a manner so that the charge is brought back to its mean position. Remember the concept that we had in terms of spring block system, and I discussed in detail about stable and unstable equilibrium, right? So if I disturb it from the mean position, so this is the mean position, if I disturb it left or right, the tendency of the charge should be to come back towards its mean position. Then this charge will be said to be in stable equilibrium. Is this clear? Okay. Now let us see. Let's try to displace it slightly over it. Let's say I brought this charge somewhere over a small displacement. I placed it over. Now you see what has happened. Now the repulsion because of this, because of the charge which is present at 1, will be in this direction, and this repulsion is going to certainly increase. Why it is going to increase? Because this distance has decreased, right? So as we know that this force, that is the force of electrostatic that exists between two charges, is inversely proportional to square of the distance between them. So this force, that is F1, is certainly going to increase. What about F2? Now if you see the repulsive force because of the charge which is present at point number 2, obviously is going to decrease. Why it's going to decrease? Because the distance has increased. So this is going to decrease. This is F2. Now, if I ask you, what is the direction of the net force? What is the direction of the net force? So at this point, the direction of the net force is this. That is, this is F net. Correct? That is towards the mean position. Towards the mean position. Which means that it is telling us that it should be in stable equilibrium, isn't it? Right? The net force, once you displace it from the mean position, it's again trying to get it back to the mean position, and that was the condition, that was the situation we have seen in case of equilibrium. And what kind of equilibrium? Stable equilibrium. So if you move a charge along one direction, you see that it is having a tendency to move again back towards its mean position, which is demonstrating that it is under a stable equilibrium condition. Let's check it. If I shift it on this side, let's say I shift it over here a little bit. Now what will happen? See, the force of repulsion because of this charge number 2 is going to increase. Correct? The force of repulsion, let me just draw it over here because I'm sure that you must have drawn the first case. So this F2 will now increase and F1 will now decrease. Correct? What is the direction of the net force? The net force is in this direction, which is towards the mean position, right? So whether you displace it left or right, the charge which is present at point number 3 is in stable equilibrium, right? It is in stable equilibrium. Understand this demonstration because see, it might be asked in terms of a question, it might be asked in terms of a concept. We might have to use this in a particular problem, we never know. So let's say you displace it slightly, now you can have an analysis of the forces, and now you know that the net force will be towards this direction only if you shift it slightly towards this charge which is present at 1, okay? If you shift it in the other direction also, as we have seen, the net force will again try to bring it back to its initial condition or to its equilibrium condition, okay? So it is under a state of what kind of equilibrium? Stable equilibrium. Clear with this? Okay. So this is under a state of stable equilibrium. So we say that if we have got a system of 3 charges such that the charges which are present at these 2 points are fixed, both of them are equal, and if we place another charge at the center of the line joining the 2 charges, along the line joining the 2 charges, the third charge will be in a condition of stable equilibrium. Along which line? Along the line joining the 2 charges. What if I would have displaced it along the line perpendicular to the line joining the 2 charges? Then what would happen? Will it still be a case of stable equilibrium or not? All right, that is something that is interesting. That is what we are going to study next. But before that, we know another type of equilibrium, that is unstable equilibrium. So what is unstable equilibrium? If I talk in terms of charge, I can certainly say that when a charge is displaced slightly from its position, the force on it does not try to bring it back to its initial equilibrium position, right? Okay, it actually displaces the charge further away from the equilibrium position. Then we say that this particular charge is under a unstable equilibrium condition. Okay, how about, we have seen that what happens in case if you displace this charge along the line joining the 3 charges. What if we displace this charge perpendicular to the line joining the 3 charges, which means I'm talking about displacing it along this line. Okay, now let's say I displaced it over here. I displaced this positive charge over here. Now what will happen? The force of repulsion will act along this line, so this will be F1 and this will be F2, of course. This will be F2. Both of them are equal because the distance is going to be equal, right? What is more interesting is that the net force will be in this direction. This is the net force, right? So it is nowhere taking it again back towards the equilibrium position. Rather, it is displacing it away from its equilibrium position, isn't it? So it is under a state of unstable equilibrium condition. Even if you take this down, something similar happens. If you take this positive charge over here, you know that the force of repulsion will be along this direction because of the first one, this is F1, and force of repulsion is along this direction because of the second one, so F2. Net force you'll get along this, right? Of course, because we know F1 is equal to F2, right? So it is taking it away from its equilibrium condition, so it is under a state of unstable equilibrium. Clear with this? Easy, no? So you know now that in which condition, if you are taking a system of three charges where all the three are positive and of course they are equal, these charges are fixed, and only this charge which is at point number 3 is supposed to move. So initially we started off with a condition where all the two fixed charges were equal in magnitude and of course in nature as well, that is both of them are positive. If I introduce a positive charge in between, then I see that along the line joining the two charges, if you displace this, it is under a state of stable equilibrium, while if you have displaced it perpendicular to the line joining the two charges, it is under a state of unstable equilibrium. No problem. So we discussed that, we have checked that out, no problem at all. Okay.